Right now, at this very moment, you believe something is happening. You believe that the seconds are ticking away, that the present moment is real, that the past is behind you, and the future is ahead of you. You believe that time is carrying you forward, like a river that never stops flowing. You wake up, you go through your day, you fall asleep, and you believe that time moved you from morning to night. You look at the clock on your wall, and you trust it. You look at the calendar on your phone, and you trust it. You celebrate birthdays because you believe another year has passed. You mourn the dead because you believe their time has ended. Everything in your life, every single decision you have ever made, every memory you have ever formed, every plan you have ever constructed for tomorrow is built on one single assumption. That time is real. That time exists. That time is actually out there, flowing, moving, carrying the universe forward from one moment to the next. But here is the thing. Some of the most brilliant physicists alive today, people who have spent their entire careers studying the deepest structure of reality, people who understand the mathematics of the universe better than almost anyone else on this planet. These people are now telling us something that sounds absolutely insane. They are telling us that time might not actually exist, not in the way you think it does, not in the way anyone thinks it does, and possibly not at all. Now, before you dismiss this as some kind of abstract philosophical game, before you say this is just scientists being weird, let me give you a few facts that should stop you in your tracks. Fact number 1. The most fundamental equation in all of quantum gravity, the equation that is supposed to describe the quantum state of the entire universe, the Wheeler-DeWitt equation, has no variable for time. Time is simply absent. It does not appear. The equation that describes reality at its deepest level says nothing about time whatsoever. Fact number 2. Albert Einstein proved, over 100 years ago, that time is not the same everywhere. Your head ages faster than your feet. Not metaphorically, literally. Atomic clocks at different heights tick at different rates, and this has been measured and confirmed in laboratories. Fact number 3. Almost all the fundamental laws of physics work perfectly, whether time moves forward or backward. If you filmed a subatomic interaction and played the film in reverse, the physics would look completely valid. The universe, at its most fundamental level, does not seem to know which direction time is supposed to go. Fact number 4. In 1908, a philosopher at Cambridge University named J.M.E. McTaggart published a paper called The Unreality of Time, in which he used pure logic to argue that time cannot possibly exist. For over a century, philosophers debated his argument, and now, over 100 years later, physics appears to be arriving at the same conclusion through a completely different route. Fact number 5. According to one of the most respected interpretations of Einstein's own theory of relativity, the dinosaurs are still alive right now. You are still being born right now, and your death has already happened. All of these events exist simultaneously in a frozen four-dimensional block that we call spacetime. There is no flow. There is no passage. There is no moving present moment. Everything just is. If any of that made your brain hurt, good. That means you are paying attention, because this is not science fiction. This is not a thought experiment. These are real results from real physics, published in real scientific journals by real physicists with real credentials. And today, we are going to go through all of it. Every single layer, from the ancient philosophers who first questioned the nature of time, to Isaac Newton who thought he had it figured out, to Albert Einstein who destroyed Newton's version of time and replaced it with something far stranger, to the quantum physicists of the 20th and 21st centuries who are now suggesting that even Einstein's version of time might not survive. We are going to look at what the experiments actually show, what the mathematics actually says, what your own brain is actually doing when it creates the experience of time, and what all of this means for you, for the universe, and for the nature of reality itself. This is going to be a long journey. It is going to be deep. It is going to challenge things you have believed your entire life. And I promise you, by the end of it, you will never look at a clock the same way again. So if you are the kind of person who genuinely wants to understand how the universe works, if you are someone who is not satisfied with surface-level answers, then subscribe to this channel right now, hit that like button, turn on the notification bell, and drop a comment telling me your honest gut feeling. Do you think time is real? Let us find out together. Let us start with the most basic question imaginable. What is time? It seems like such a simple question. We use the word constantly. We say things like, I do not have enough time, or time flies, or give me a moment. We schedule our lives around time. We divide our existence into seconds, minutes, hours, days, years, centuries. We have clocks in every room, watches on our wrists, timestamps on every message we send. Time is everywhere. It is the backdrop of everything we do, so surely we must know what it is. But here is the strange truth. Nobody has ever been able to define time in a way that actually holds up under scrutiny. St. Augustine, one of the greatest thinkers in Western history, wrote about this in his Confessions around the year 400 AD. He said something that has haunted philosophers and physicists ever since. He said, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." That was 1600 years ago. And today, in the 21st century, we are still in the same position. We all feel time. We all experience time. But when you actually try to pin down what time is, as a thing, as a substance, as a feature of reality, it slips through your fingers like smoke. Think about it for a moment. When you say that time passes, what exactly is passing? When you say that an hour went by, what went by? Where did it go? You can point to space. You can say, here is a meter of space, and you can measure it with a ruler. But can you point to time? Can you hold a second in your hand? Can you show someone what a minute looks like? You cannot. You experience the effects of what you call time. You see things change. You see a flower bloom, then wilt, then decay. You see a child grow into an adult, then grow old. You see the sun rise and set. But are you actually observing time itself? Or are you observing change, and then labeling that change with the word time? This distinction is not a minor philosophical nitpick. It is actually the central question, because there is a very real possibility that what we call time is nothing more than a label we have invented to describe the fact that things change. And if that is the case, then time is not a feature of the universe at all. It is a feature of our description of the universe. It is a word, a concept, a tool, but not a thing that actually exists out there in reality. The earliest human civilizations did not have clocks. They did not have calendars in the way we understand them. What they had was observation. They observed that the sun moved across the sky. They observed that the moon went through phases. They observed that the seasons repeated. They observed that things grew, aged, and died. And from these observations, they began to construct systems of measurement. They invented sundials, which tracked the movement of shadows. They invented water clocks, which measured the flow of water from one vessel to another. They invented hourglasses, which measured the fall of sand. But notice what all of these devices have in common. They do not measure time directly. They measure change, the movement of a shadow, the flow of water, the fall of sand, and then they map that change onto a scale and call it time. The question that no ancient civilization ever answered, and that we have still not answered today, is whether time is the thing causing the change, or whether change is the thing causing our concept of time. Now, for most of human history, people assumed that time was real, fundamental, and absolute. And the person who made this assumption most explicit, who built an entire system of physics around it, was Isaac Newton. In 1687, Newton published his masterwork, the Philosophiae Naturalis Principia Mathematica. In it, he laid out his laws of motion and his theory of gravity, which together formed the foundation of classical physics for over 2 centuries. But Newton also made a very specific claim about time. He wrote, and I quote, "Absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external." Read that sentence carefully. Newton is saying that time is absolute. It is the same everywhere, for everyone, at all times. It flows at a constant rate, and it has nothing to do with anything else in the universe. It just flows. On its own, by its own nature. In Newton's view, time is like a cosmic stage. The universe is a theatre, and time is the stage on which all events are performed. The actors come and go, the scenes change, but the stage itself is eternal, unchanging, and independent of anything happening on it. This view of time is incredibly intuitive. It matches our everyday experience perfectly. When you look at a clock, you believe that the clock is measuring something real, something external, something that would exist even if the clock were not there. You believe that the same amount of time passes for everyone, everywhere. You believe that 1 second in New York is the same as 1 second in Tokyo, the same as 1 second on the moon, the same as 1 second on a distant star. This is Newton's time. Absolute, universal, constant, and flowing. And for over 200 years, nobody seriously questioned it. Newton's physics worked. His equations predicted the motion of planets, the trajectories of cannonballs, the behavior of tides. If his concept of time was wrong, why did everything work so well? This is the power of Newton's legacy. His version of time became so deeply embedded in human thinking that most people alive today still believe it, even though it was proven wrong over a century ago. Now, before Einstein came along and demolished Newton's time, there was an important philosophical challenge that is worth examining. In 1908, a philosopher at Cambridge University named John McTaggart Ellis McTaggart published a paper in the journal Mind with a deceptively simple title, The Unreality of Time. In this paper, McTaggart made an argument that has never been fully refuted and that still provokes debate among philosophers to this day. McTaggart's argument goes like this. There are two ways to describe events in time. The first way, which he called the A series, describes events in terms of past, present, and future. For example, the dinosaurs going extinct is in the past. You reading this right now is in the present. The heat death of the universe is in the future. The A series is dynamic. Events move. Something that is in the future becomes present, and then becomes past. This is what we mean by the flow of time. The second way, which McTaggart called the B series, describes events in terms of earlier than and later than. The dinosaurs going extinct is earlier than the moon landing. The moon landing is earlier than you reading this. This ordering is fixed. It does not change. The dinosaurs will always be earlier than the moon landing. The B series is static. Now here is McTaggart's argument. For time to be real, the A series must be real, because the B series alone just gives you a static ordering. It gives you before and after, but it does not give you change, it does not give you flow, it does not give you the passage of time. Without the A series, there is no moving present moment, no transformation of future into present into past. There is just a frozen order. But the A series, McTaggart argued, is contradictory. Here is why. Every event has all three properties. It is past, it is present, and it is future. The extinction of the dinosaurs was once in the future, it was briefly in the present, and it is now in the past. But an event cannot logically be past and present and future all at the same time. These properties are mutually exclusive. Something cannot be both in the past and in the present. That is a contradiction. Now, you might respond by saying, well, the event is not past, present, and future at the same time. It is future, then present, then past, at different times, but McTaggart pointed out that this response is circular. You are using the concept of time, specifically different times, to resolve a contradiction about time. You are saying the A series works because events have different A properties at different A times. But this just pushes the problem back. Those different A times themselves have A properties, and those A properties lead to the same contradiction. And resolving that contradiction requires appealing to yet another level of A times, and so on, to infinity. The argument is either contradictory or infinitely circular. Either way, the A series fails. And if the A series fails, then time has no passage. And if time has no passage, then in McTaggart's view, time is unreal. What we call time is just a static ordering of events, not a flowing dynamic reality. McTaggart published this argument in 1908. Many philosophers have tried to refute it. None have done so conclusively. The argument remains one of the most discussed and debated in all of philosophy. And what makes it particularly fascinating is that physics, as we will see, has been arriving at a remarkably similar conclusion through completely independent means. Now let us move to the moment that changed everything. Let us move to 1905 and to a 26-year-old patent clerk working in Bern, Switzerland. His name was Albert Einstein, and in that single miraculous year, he published 4 papers that would transform physics forever. One of those papers introduced the special theory of relativity, and with it, Newton's absolute time was destroyed. Einstein's special relativity is built on two simple postulates. First, the laws of physics are the same for all observers moving at constant velocity relative to each other. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. These two postulates seem harmless enough. But when you combine them and work out the mathematical consequences, you get results that are absolutely shocking. The first shocking result is time dilation. If you are moving relative to me, your clock ticks slower than mine, not because your clock is broken, not because there is something wrong with your clock, but because time itself, the actual rate at which physical processes occur, is slower for you than it is for me. This is not a trick, not an illusion, not a matter of perception. It is a real, physical, measurable effect. Let me give you a concrete example. Imagine two twins. Let us call them Alice and Bob. Alice stays on Earth. Bob gets on a spaceship and travels at 90% of the speed of light to a distant star, then turns around and comes back. When Bob returns, he finds that he has aged, let us say, 10 years. But Alice has aged 23 years. Bob is physically, biologically younger than his twin sister, not because he used some anti-aging cream, not because of a medical procedure, but because time literally passed more slowly for him while he was moving at high speed. This is the famous twin paradox, and it is not actually a paradox at all. It is a straightforward prediction of special relativity, and it has been confirmed by every experiment ever designed to test it. One of the most elegant confirmations comes from muon particles. Muons are subatomic particles that are created when cosmic rays from outer space hit molecules in Earth's upper atmosphere. Muons are unstable. They have a very short half-life of about 2.2 microseconds. Given their speed, even though they travel close to the speed of light, they should decay long before they reach Earth's surface. The math is straightforward. In 2.2 microseconds, even at nearly light speed, a muon should only travel about 660 meters. But the atmosphere is many kilometers thick, so most muons should disintegrate long before they reach the ground. Yet they do not. We detect enormous numbers of muons at ground level. Why? Because of time dilation. From our perspective on the ground, the muon's internal clock is running slow. Its 2.2 microsecond lifetime is stretched out, giving it enough time to reach the surface. From the muon's perspective, it lives for the normal 2.2 microseconds, but the distance to the ground is length contracted, so it does not need as much time. Either way, the result is the same. Special relativity is correct, and time is not the same for everyone. But muons are subatomic particles. What about real clocks? What about actual human-scale time measurement? In 1971, physicists Joseph Hafele and astronomer Richard Keating performed one of the most famous experiments in the history of physics. They took 4 cesium-beam atomic clocks and put them on commercial airplanes. One set of flights went eastward around the world. Another set went westward. When the clocks came back, they were compared to reference clocks that had stayed on the ground. The results matched Einstein's predictions precisely. The eastward travelling clocks had lost 59 nanoseconds. The westward travelling clocks had gained 273 nanoseconds. These are tiny differences, but they are real, measurable, and exactly what relativity predicted. Time does not tick at the same rate for objects in different states of motion. Now, time dilation due to speed is dramatic enough, but Einstein's special theory of relativity also gives us something even more mind-bending, the relativity of simultaneity. And this is where things start to get truly disturbing. In everyday life, you assume that 2 events that happen at the same time for you also happen at the same time for everyone else. If a firecracker goes off in New York and another firecracker goes off in London at exactly the same moment according to your watch, you assume that everyone would agree those 2 events were simultaneous. But special relativity says this is wrong. 2 events that are simultaneous for one observer are not simultaneous for another observer who is moving at a different velocity. This is not a matter of perception or signal delay or measurement error. It is a fundamental feature of reality. Simultaneity is relative. There is no objective, universal now. Einstein illustrated this with a thought experiment. Imagine you are standing in the middle of a train platform. Lightning strikes both ends of the platform at the exact same moment. You see both flashes at the same time, so you conclude the strikes were simultaneous. But now, imagine someone is on a train moving through the station at high speed. This person is also in the middle of the train at the moment the lightning strikes. But because the train is moving, this person is moving towards the flash from the front of the train and away from the flash from the back. So this person sees the front flash first and the back flash second. And here is the crucial point. This is not because the person on the train is confused or making an error. Within the framework of special relativity, both observers are equally correct. For the platform observer, the strikes were simultaneous. For the train observer, they were not. Neither observer has a more true version of events. Simultaneity depends on your state of motion. The consequences of this are staggering. If there is no universal now, then there is no single present moment that is real for everyone. Your present moment is literally someone else's past and someone else's future, depending on how they are moving relative to you. Roger Penrose, one of the greatest mathematical physicists of the 20th century, illustrated this with what is now called the Andromeda paradox. Consider two people passing each other on the street. One person is walking toward the Andromeda galaxy, which is about 2.5 million light-years away. The other person is walking away from the Andromeda galaxy. These people are walking at ordinary human speeds, just a few kilometers per hour. But because of the enormous distance to Andromeda, the relativity of simultaneity means that these two people disagree about what is happening right now in Andromeda by several days. One person's present includes an event in Andromeda that, for the other person, has not happened yet, and neither person is wrong. According to the mathematics of special relativity, both are equally correct about what is happening now. This is real. This is not a thought experiment that only applies in theory. The mathematics is unambiguous. If two observers disagree about what is happening now, and both are equally correct, then the concept of now has no objective meaning. And if now has no objective meaning, then the distinction between past, present, and future has no objective meaning either. And this leads us to something truly extraordinary. In 1907, just 2 years after Einstein published Special Relativity, his former mathematics teacher, Hermann Minkowski, gave a famous lecture in which he said something that has echoed through physics ever since. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." What Minkowski realized was that Einstein's special relativity was telling us that space and time are not separate things. They are aspects of a single entity, space-time, a four-dimensional fabric in which 3 dimensions are spatial and 1 dimension is temporal, and all 4 are woven together into a single unified structure. This was not just a mathematical convenience. Minkowski showed that the geometry of space-time is real. Events do not happen in space and in time separately. They happen in space-time. And the distance between 2 events in space-time is not a simple spatial distance or a simple time interval. It is a space-time interval, a quantity that mixes space and time together in a specific mathematical way. And this space-time interval is invariant. All observers agree on it, regardless of their state of motion. Even though they disagree on distances and duration separately, they agree on the space-time interval. This tells us something profound. Space and time, on their own, are observer-dependent. They are relative. They are not fundamental. But space-time, the unified structure, is observer-independent. It is absolute. It is fundamental. Time, by itself, is not a thing. It is merely one observer-dependent aspect of the deeper entity called space-time. But Einstein was not done. Special relativity only deals with objects moving at constant velocity in the absence of gravity. In 1915, Einstein published his general theory of relativity, which extended special relativity to include gravity and acceleration. And this theory demolished what was left of Newton's time even more completely. General relativity is based on a breathtaking idea. Gravity is not a force. Newton thought gravity was a force that massive objects exerted on each other across empty space. The Earth pulls on the moon. The Sun pulls on the Earth. But Einstein showed that this picture is wrong. Gravity is not a force at all. It is the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space-time around them. Other objects then follow the curves of this bent space-time, which we perceive as gravitational attraction. The Earth does not pull on you. The Earth curves the space-time around it, and you follow that curve. The reason you stick to the ground is not because a force is pulling you down. It is because the space-time in which you exist is curved, and the natural path through curved space-time keeps you on the surface. And here is where it gets directly relevant to our question about time. General relativity tells us that the curvature of space-time affects time. Time runs slower in stronger gravitational fields. This is called gravitational time dilation, and it is a real, measured, confirmed effect. Let me give you the most practical example possible: the Global Positioning System, GPS, the technology that allows your phone to know where you are on Earth, to within a few meters. GPS works by using signals from a network of satellites orbiting the Earth. Each satellite carries an extremely precise atomic clock. Your phone receives signals from multiple satellites, and, by comparing the times of arrival, calculates your position. But here is the thing. The satellites are in orbit, about 20,200 kilometers above the Earth's surface. At that altitude, they are in a weaker gravitational field than clocks on the ground. General relativity tells us that their clocks should tick faster than ground-based clocks by about 45 microseconds per day. At the same time, the satellites are moving at high speed, which creates a special relativistic time dilation that slows their clocks by about 7 microseconds per day. The net effect is that the satellite clocks gain about 38 microseconds per day relative to ground clocks. Now, 38 microseconds sounds tiny, but at the speed of light, which is the speed at which GPS signals travel, 38 microseconds corresponds to about 10 kilometers of distance error per day. If GPS did not correct for relativistic time dilation, your phone's navigation would be off by 10 kilometers every day, and the error would grow continuously. The GPS system must correct for Einstein's time dilation in order to function. You use a practical application of the non-universality of time every single time you use a map on your phone. But GPS is just the beginning. Scientists at the National Institute of Standards and Technology, NIST, in the United States have used ultra-precise optical atomic clocks to measure gravitational time dilation at incredibly small scales. In 2010, they demonstrated that raising a clock by just 33 centimeters, about 1 foot, produces a measurable difference in the rate of time. The clock at the higher altitude ticked faster than the clock at the lower altitude, by an incredibly tiny amount, but a real, measurable amount. This means that your head, which is about a meter higher than your feet, ages faster than your feet. Over your lifetime, the difference is negligibly small, but it is real. Time is literally not the same at the top of your body as it is at the bottom. These are not theoretical predictions waiting for confirmation. These are measured results. They have been repeated in laboratories around the world. Time dilation, both gravitational and velocity-based, is one of the most thoroughly tested and confirmed predictions in all of physics. And what it tells us is unequivocal. Time is not universal. Time is not constant. Time does not flow at the same rate everywhere. Time depends on where you are, how fast you are moving, and how strong the gravitational field is around you. Newton's absolute, universal, constantly flowing time is not just wrong, it is spectacularly wrong. Now, once you accept that space and time are unified into space-time, and that this space-time is curved by mass and energy, a very natural question arises. What does the universe look like from the perspective of space-time? If we take seriously the idea that all of space-time is a single four-dimensional structure, then what does that structure look like as a whole? And this is where we arrive at one of the most profound and disturbing ideas in all of physics, the block universe. The block universe is a direct consequence of special and general relativity, combined with the relativity of simultaneity. The argument, which was formalized by philosophers Riet, Dike and Putnam in the 1960s, goes like this. We have already established that there is no universal present moment. Different observers in different states of motion disagree about which events are happening now. If observer A says event X is happening now, observer B, who is moving differently, might say event X has already happened, while observer C might say event X has not happened yet. and all three are equally correct. Now, if event X is real according to observer A, who says it is in the present, then it must also be real according to observer B, even though B says it is in the past. Because you cannot say something is real for one observer but not for another. Reality is not observer-dependent in that way. And the same argument applies in the other direction. If event X is in B's past, and it is real, then all events that B considers present must also be real. But some of B's present events are in A's future, so A's future events must also be real. Follow this chain of reasoning to its logical conclusion, and you get an extraordinary result. All events, past, present, and future, are equally real. They all exist. The entire history of the universe, from the Big Bang to the heat death, is laid out in a four-dimensional block. Nothing comes into existence, nothing goes out of existence. There is no flow, there is no passage. The block just is. In this picture, the universe is like a loaf of bread. Each slice of the loaf is a three-dimensional snapshot of the universe at one moment. The past slices exist. The present slice exists. The future slices exist. They are all equally real, equally solid, equally there. The only thing that distinguishes them is their position within the four-dimensional block. Your birth is in one slice. Your death is in another slice. Both slices exist, right now, simultaneously, in the block. Albert Einstein himself appears to have been sympathetic to this view. In 1955, when his lifelong friend Michel Besso died, Einstein wrote a letter to Besso's family. In that letter, he wrote, "Now he has departed from this strange world a little ahead of me. That signifies nothing." For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein wrote this just weeks before his own death. He seems to have genuinely believed that the distinction between past, present, and future is not a feature of reality, but an illusion of human consciousness. Now, the block universe is not without its critics. Many philosophers and some physicists push back against it. They argue that the relativity of simultaneity does not necessarily imply that all times are equally real. There are alternative interpretations of relativity that try to preserve a genuine present moment. The philosophical position called presentism holds that only the present exists, and the past and future are not real. But presentism has a serious problem with relativity, because relativity says there is no universal present. If there is no universal present, then presentism cannot identify which slice of the block is the real one. Another position, called the growing block, holds that the past and present exist, but the future does not yet. The block grows as time passes. This is an attempt at a compromise, but it also struggles with the relativity of simultaneity. The honest truth is that this debate is not settled. Physicists and philosophers are still arguing about it, but the mathematical structure of relativity very naturally and elegantly supports the block universe interpretation. And if the block universe is correct, then time, as a flowing river carrying us from past to future, does not exist. What exists is a static four-dimensional structure, and the feeling of flow, the feeling of now, the feeling that the present moment is special, is something your consciousness creates, not something the universe provides. Let this sink in for a moment. According to the block universe, the dinosaurs are not gone. They are still there, in their slice of the block. The Roman Empire has not fallen. It is still there. World War II is still happening. Your childhood is still happening. Your death has already happened. None of these events have vanished into non-existence, or are waiting to come into existence. They all exist, all the time, in the eternal, unchanging block of space-time. The flow of time is an illusion. The passage from past to future is something your brain constructs. Reality itself is timeless. Now, if Einstein's relativity dismantled Newton's time and gave us the block universe, you might think that quantum mechanics, the other great pillar of modern physics, would have something to say about all this. And it does, but what it says makes the situation even more confusing. In quantum mechanics, time plays a very strange role. In the standard formulation of quantum mechanics, there is an equation called the Schrödinger equation. This equation describes how the quantum state of a system evolves over time. It is the quantum equivalent of Newton's laws of motion, and it works spectacularly well. Quantum mechanics is arguably the most successful theory in the history of science. It has been tested to incredible precision and has never been found wrong. But there is something deeply peculiar about how the Schrödinger equation treats time. In quantum mechanics, every physical quantity that you can observe, like position, momentum, energy, spin, is represented by what is called an operator. You can measure these quantities. They are observables. But time is not an operator. Time is not an observable. Time is what physicists call a parameter. It is a background label that you plug into the equation from the outside. It is like the stage on which the quantum drama plays out. You do not measure time in the same way you measure position or momentum. You just assume it is there and use it as a framework. This is a problem, because general relativity says time is dynamic, flexible, and responsive to matter and energy. But quantum mechanics says time is fixed, rigid, and external. These two descriptions are incompatible. Relativity treats time as part of the system, something that is affected by physics. Quantum mechanics treats time as outside the system, something that physics happens within. They cannot both be right. This incompatibility is one of the deepest problems in all of physics, and it is one of the main reasons why we do not yet have a unified theory of quantum gravity, a single theory that combines general relativity and quantum mechanics into one coherent framework. Finding such a theory is often described as the holy grail of theoretical physics, and when physicists attempt to construct such a theory, something extraordinary happens. Time disappears. In 1967, physicists Wheeler-DeWitt and John Archibald Wheeler derived what is now known as the Wheeler-DeWitt equation. This equation is the result of applying the principles of quantum mechanics to the entire universe, including its gravitational field. In other words, it is the equation that should describe the quantum state of the whole cosmos. And the Wheeler-DeWitt equation has a stunning feature. There is no time variable in it. None. The equation is entirely static. It does not describe a universe that evolves from one moment to the next. It describes a universe that simply is. The wave function of the universe, as described by the Wheeler-DeWitt equation, is timeless. It does not change. There is no before and after. There is no evolution. There is just a static quantum state, frozen, unchanging, eternal. When DeWitt first derived this equation and realized that time was absent, he was reportedly stunned. He checked the math again and again. But the result was clear. When you quantize gravity, when you apply quantum mechanics to space-time itself, time vanishes. The equation that describes reality at its deepest level does not contain time. This is not a minor technical detail. This is telling us something profound about the nature of reality. The most fundamental description of the universe, the equation that unifies quantum mechanics and general relativity at the level of the whole cosmos, says that the universe is timeless. Time is not part of the fundamental picture. Whatever time is, it is not written into the deepest level of reality. John Wheeler, one of the most creative physicists of the 20th century, once made a famous remark about time. He said, "Time is what prevents everything from happening at once." It is a clever quip. But the Wheeler-DeWitt equation seems to be saying that, at the most fundamental level, everything is happening at once. Or more precisely, nothing is happening at all, because happening requires time, and time is not there. Now, if the fundamental equation of quantum gravity says the universe is timeless, and yet we clearly experience time, feel time, measure time, live in time, then where does the experience of time come from? How do you get from a timeless equation to a world that feels like it is flowing forward from past to future? This is called the problem of time, and it is one of the most important unsolved problems in theoretical physics. Different physicists have proposed different solutions, and some of the most fascinating ideas come from the work done in the 1980s and beyond. In 1983, two physicists named Don Page and William Wouters published a remarkable paper. They proposed a mechanism by which time could emerge from a timeless universe. Their idea is beautiful in its simplicity. Imagine the universe as a whole is in a static quantum state, exactly as the Wheeler-DeWitt equation says. No time, no evolution, no change. But now consider two subsystems within this universe. One subsystem acts as a clock. The other subsystem is everything else, the thing that the clock is supposed to measure the time of. Page and Wouters showed that if these two subsystems are quantum entangled with each other, Then, from the perspective of an observer inside the universe, using the clock subsystem to track the other subsystem appears to evolve in time. Change appears, motion appears, events seem to flow from past to future. But here is the key. From the perspective of an observer outside the universe, looking at the whole thing, nothing is changing. The total state is static, exactly as the Wheeler-DeWitt equation says. Time is not fundamental. It is emergent. It arises from the quantum correlations, the entanglement, between subsystems within a timeless whole. Think of it this way. Imagine a photograph. A single photograph does not move. It does not change. It is static. But now imagine that the photograph contains two clocks, and the hands of the two clocks are correlated in a specific way. If you look at just one clock and use it to track the position of the other, you can construct a story of change. You can say, when this clock read 1, that clock read 2, and when this clock read 2, that clock read 3. You have created the appearance of evolution, the appearance of time, from a completely static picture. The time is not in the photograph. The time is in the correlation between the two clocks. The Page-Wouters mechanism is not just a theoretical curiosity. In 2013, researchers at the Istituto Nazionale di Ricerca Metrologica, INRIM, in Turin, Italy, performed an experiment that demonstrated this mechanism using entangled photons. They created a system of entangled photons and showed that from an internal perspective, using one photon as a clock, the other photon appeared to evolve in time. But from an external perspective, looking at the whole entangled system, the state was static. Time emerged from entanglement. This is published, peer-reviewed, experimental science. It is one of the most remarkable experiments in the history of physics, and most people have never heard of it. The Page-Wouters mechanism does not prove that time is an illusion, but it proves something almost as significant. Time does not need to be fundamental. You can start with a completely timeless universe and derive the appearance of time from quantum entanglement. This means that the experience of time flowing, of events evolving, of the present moment moving forward, could be an emergent phenomenon, not a fundamental feature of reality. Now, there is another deeply disturbing fact about time that we need to address, and this one comes not from quantum gravity or relativity, but from the basic structure of the laws of physics themselves. Almost all the fundamental laws of physics are time reversal symmetric. This means that if you take any fundamental physical process and run it backward in time, the result is also a valid physical process. Newton's laws of motion are time symmetric. If you film a ball flying through the air and play the film backward, the backward trajectory is a perfectly valid Newtonian trajectory. Maxwell's equations of electromagnetism are time symmetric. The Schrödinger equation of quantum mechanics is time symmetric. Even Einstein's equations of general relativity are time symmetric. At the most fundamental level, the laws of physics do not distinguish between the past direction and the future direction. They work equally well in both directions. This is profoundly strange, because in our everyday experience, there is a very clear difference between past and future. Eggs break but do not unbreak. Coffee cools but does not spontaneously reheat. People age but do not grow younger. Buildings crumble but do not spontaneously assemble. The world around us has an obvious directionality, an obvious arrow pointing from past to future. But the fundamental laws of physics, the laws that govern every particle and every interaction in the universe, have no such arrow. They are perfectly symmetric in time. There is also a deeper symmetry at play here. In particle physics, there is a theorem known as the CPT theorem. CPT stands for charge conjugation, parity, and time reversal. The CPT theorem states that any physical process remains valid if you simultaneously replace all particles with their antiparticles, reflect everything in a mirror, and reverse the direction of time. This combined symmetry, CPT symmetry, is believed to be absolutely fundamental. It has never been observed to be violated, and there are strong theoretical reasons to believe it cannot be violated. The CPT theorem tells us that time reversal is built into the deepest structure of physics. The universe, at its most fundamental level, does not care which direction time goes. So if the laws of physics do not distinguish between past and future, where does the arrow of time come from? Why do we experience time as flowing in one direction? Why does the past feel different from the future? This is one of the deepest questions in all of science. The answer as far as we currently understand it, comes from thermodynamics, specifically from the second law of thermodynamics and the concept of entropy. Entropy is a measure of the disorder, or more precisely, the number of microscopic arrangements consistent with a given macroscopic state. A low entropy state is one where things are highly ordered. A high entropy state is one where things are highly disordered. The second law of thermodynamics states that the entropy of a closed system tends to increase over time. Things naturally go from order to disorder. This is the only law of physics that distinguishes between the past and the future. All other laws are time-symmetric. Only the second law of thermodynamics gives us an arrow. The arrow of time is the increase of entropy. Consider an egg sitting on the edge of a table. The egg is in a relatively low entropy state. It is ordered, structured, intact. When the egg falls and shatters on the floor, it moves to a high entropy state. The pieces are disordered, scattered, broken. The second law says that the reverse process, a shattered egg spontaneously reassembling itself and jumping back onto the table, is extraordinarily unlikely. Not impossible technically, but so overwhelmingly improbable that it would never happen in the entire age of the universe. The reason is statistical. There are astronomically more ways for the egg to be shattered than for it to be intact. The transition from intact to shattered is overwhelmingly more probable than the reverse. Ludwig Boltzmann, the great Austrian physicist of the 19th century, was the person who first understood this clearly. Boltzmann showed that entropy is fundamentally about probability. High entropy states are overwhelmingly more probable than low entropy states. A system will naturally evolve toward higher entropy simply because there are so many more high entropy states available. It is not that there is a law forcing things toward disorder, it is just that disorder is overwhelmingly more likely. And here is Boltzmann's crucial insight about the arrow of time. We perceive time as flowing in a particular direction because we live in a universe where entropy is increasing. The arrow of time is the arrow of entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because memories are records which require low entropy to form. We cannot remember the future because future events correspond to higher entropy states that have not left records yet. But this immediately raises a monumental question. If the arrow of time is just the direction of increasing entropy, and if entropy increases because low entropy states evolve toward high entropy states, then why was the universe in a low entropy state to begin with? Why did the Big Bang start with incredibly low entropy? If high entropy is overwhelmingly more probable, then a low entropy Big Bang is extraordinarily unlikely. So why did it happen? This is what philosophers call the past hypothesis. The term was coined by philosopher David Albert, and the idea has been developed extensively by physicist Sean Carroll. The past hypothesis simply states that the universe began in an extremely low entropy state. This is not a prediction of any physical law. It is an initial condition. It is a boundary condition. It is something you have to put in by hand at the beginning of the universe. No current physical theory explains why the universe started with low entropy. We just observe that it did. Sean Carroll has argued this point with exceptional clarity. He says that the arrow of time is not a fundamental law of physics. It is a consequence of special initial conditions. The universe happened to start in a very ordered, very low entropy state, and everything since then has been a process of that order unwinding, of entropy increasing, of the universe moving towards its most probable state. If the initial conditions had been different, if the Big Bang had been high entropy instead of low entropy, there would be no arrow of time. There would be no distinction between past and future. There would be no flow. This means that the most fundamental seeming feature of time, the fact that it flows in a particular direction, might not be fundamental at all. It might be a cosmic accident, a consequence of how the universe happened to begin, not a deep truth about reality, but a contingent fact about initial conditions. Carroll has spent decades working on this problem, trying to find a cosmological scenario in which the low entropy initial state is explained by the dynamics, rather than being inserted by hand. He has proposed models in which the universe is much larger than what we observe, and different regions of this larger universe have arrows of time pointing in different directions. In some regions, entropy increases toward the future, creating an arrow of time like ours. In other regions, entropy increases in the opposite direction, creating a reversed arrow of time. In Carroll's picture, the arrow of time is a local phenomenon, not a universal one. Different parts of the universe might experience time flowing in different directions. Boltzmann himself had an even more radical idea along these lines. He proposed that the universe as a whole might be in thermal equilibrium, a state of maximum entropy where nothing happens, where there is no arrow of time, where everything is uniform and changeless. And our observable universe, with its low entropy and its arrow of time, is just a random fluctuation, a statistical accident, a temporary dip in entropy that created the conditions for complexity, for life, for consciousness, for the experience of time. This is a logically coherent idea, but it leads to a disturbing problem known as the Boltzmann brain problem. If the universe is in thermal equilibrium and our world is a random fluctuation, then what kind of fluctuation is most likely? A small fluctuation or a large one? The answer is clearly a small one. A fluctuation that creates an entire observable universe with trillions of galaxies is extraordinarily improbable. A much more probable fluctuation would create just a single brain floating in empty space, with false memories of a universe that does not exist. This is a Boltzmann brain. If Boltzmann's original hypothesis were correct, it would be overwhelmingly more likely that you are a disembodied brain with false memories than that you are a real person in a real universe. Since this seems absurd, most physicists take the Boltzmann brain problem as evidence that Boltzmann's original fluctuation hypothesis is wrong. The universe is not just a random fluctuation in a thermal equilibrium. Something else is going on. But what? That is the question. And it is a question we do not yet know the answer to. The arrow of time, it turns out, is not just a thermodynamic arrow. There are several arrows of time, and understanding how they relate to each other is a major challenge. There is the cosmological arrow, the fact that the universe is expanding rather than contracting. The expansion of the universe is one of the most well-established facts in cosmology. Since the discovery of the cosmic microwave background radiation and the observation of galaxies receding from each other, we know that the universe has been expanding for 13.8 billion years. This expansion defines a direction. The universe was smaller in the past and will be larger in the future. But is this arrow of time fundamental, or is it also a consequence of initial conditions? There is the psychological arrow, the fact that we remember the past and not the future. You can recall what you had for breakfast this morning, but you cannot recall what you will have for breakfast tomorrow. This asymmetry seems deeply built into our experience, but it is actually a consequence of the thermodynamic arrow. Memories are physical records, patterns stored in the structure of neurons. Creating and maintaining such records requires low entropy. The reason you remember the past is that the past was lower entropy, and the formation of memories is an entropy-increasing process. If the thermodynamic arrow were reversed, you would remember the future and not the past, because the future would be the low entropy direction. There is the radiative arrow, the fact that electromagnetic waves spread outward from their sources, like ripples expanding on a pond. You see light spreading out from a light bulb, not converging onto it. Ripples on a pond expand from where the stone was dropped. They do not converge from the edges toward a central point. This too appears to be connected to the thermodynamic arrow and the low entropy past. There is the quantum arrow, related to the apparent irreversibility of quantum measurement. In the standard Copenhagen interpretation of quantum mechanics, when you measure a quantum system, its wave function collapses from a superposition of multiple possibilities to a single definite outcome. This collapse appears to be irreversible. A measured state does not spontaneously unmeasure itself. But whether this is a genuine arrow of time or an artifact of the interpretation of quantum mechanics is still debated. And there is the causal arrow, the fact that causes precede effects. You push a ball, and then it moves. The push comes before the movement, not after. But is this a fundamental feature of the universe, or is it, like the other arrows, a consequence of the thermodynamic arrow? Most physicists believe that all of these arrows of time reduce to the thermodynamic arrow, and the thermodynamic arrow reduces to the past hypothesis. In other words, all the directionality we observe in the universe, every distinction between past and future, every aspect of the flow of time, may ultimately depend on one single unexplained fact: that the universe started in a state of very low entropy. If we could explain that one fact, we might understand the arrow of time. And if we could not explain it, then the arrow of time remains at its deepest level a mystery. We have now covered an enormous amount of ground. We have seen how Newton's absolute time was destroyed by Einstein. We have seen how the relativity of simultaneity eliminates a universal present. We have seen how the block universe interpretation suggests all of time exists simultaneously. We have seen how the Wheeler-DeWitt equation removes time from the fundamental equation of the universe. We have seen how the Page-Wooter's mechanism shows that time can emerge from entanglement. We have seen how the laws of physics are time symmetric. And we have seen how the arrow of time depends on unexplained initial conditions. If you are still here, you are clearly someone who cares deeply about understanding reality. So let me ask you to do something. Right now, hit that like button. It is a small action, but it makes a huge difference in how many people get to see this video. And drop a comment telling me this. At this point in the video, do you think time exists? I am genuinely curious about your answer. Now let us continue, because the most fascinating parts are ahead of us. Let us now meet the scientists who have thought most deeply about whether time is real, and who have come to some of the most radical conclusions. Julian Barber is a British physicist who spent his career outside the traditional academic establishment. He does not hold a university position. He has funded his own research for decades, working from his farmhouse in Oxfordshire, England. And he has produced some of the most profound and original work on the nature of time that anyone has ever done. In 1999, Barber published a book called The End of Time, The Next Revolution in Physics. In it, he makes an extraordinary argument. Time does not exist, not in the sense that it is an illusion that emerges from something deeper, not in the sense that it is approximate or relative, but in the fullest, most literal sense. Time does not exist at all. Barber's argument is based on a careful analysis of the Wheeler-DeWitt equation and the structure of general relativity. He introduces a concept he calls Platonia. Platonia is the space of all possible configurations of the universe. Each point in Platonia represents one complete, three-dimensional snapshot of the entire universe at one instant. Every possible arrangement of every particle, every possible state of every field is a point in Platonia. In Barber's view, Platonia is what exists, not spacetime, not time, just this vast, infinite collection of possible instantaneous configurations. Each configuration is what Barber calls a now, and these nows are all that exist. There is no time connecting one now to another. There is no flow, no passage, no evolution. The nows just are. But if there is no time connecting the nows, why do we experience the passage of time? Why do we feel like we are moving from one moment to the next? Barber's answer is remarkable. He says that some nows contain within themselves records that look like evidence of other nows. For example, one now might contain a brain with memories. Those memories are physical states of neurons. They are records within one now that happen to correspond to other nows. And the brain, being a pattern-recognizing system, interprets these records as evidence of a past. It constructs a story, a narrative of time passing, of events happening in sequence. But this narrative is a construction. The records are real, but the time they seem to point to is not. Barber uses a beautiful analogy. Imagine a collection of snapshots, like photographs, scattered on a table. Each photograph is a complete, self-contained image. Some photographs contain things that look like they are part of a sequence. A ball in the air, a ball halfway to the ground, a ball on the ground. Our minds naturally arrange these into a story. The ball fell. We infer motion, change, time. But the photographs themselves are static. They are just sitting there. There is no real motion connecting them. The motion is a story we tell ourselves based on the patterns within the photographs. In the same way, Barber argues, the nows of Platonia are static, timeless configurations. Some of them contain patterns that we interpret as evidence of change, of history, of time. But the change is not real. The history is not real. Time is not real. What is real is the pattern. What is real is the structure. What is real is the now. Barber's work is mathematically rigorous. It is directly grounded in the Wheeler-DeWitt equation and in the relational approach to physics, that goes back to Leibniz and Mach. It is not speculation. It is a serious, detailed, internally consistent proposal for what reality looks like at the deepest level. And at that deepest level, according to Barber, there is no time. Now let us turn to another physicist who has arrived at a similar conclusion through a slightly different route. Carlo Rovelli is an Italian theoretical physicist and one of the founders of loop quantum gravity. He is also one of the best science communicators in the world. His 2018 book, The Order of Time, became an international bestseller and introduced millions of readers to the idea that time might not exist. Rovelli's approach is systematic. He does not just declare that time is an illusion, he carefully peels away the layers of our concept of time, one by one, showing how each layer fails to correspond to fundamental reality. Layer 1. Time flows at the same rate everywhere. This is Newton's time, and Einstein destroyed it. Time flows at different rates in different places, depending on gravity and motion. This is experimentally confirmed. Layer 2. There is a universal present moment. This is what the relativity of simultaneity destroyed. There is no universal now. Different observers have different present moments. There is no single objective division of space-time into past, present, and future. Layer 3. The past is fundamentally different from the future. This is what time reversal symmetry challenges. The fundamental laws of physics are the same whether time runs forward or backward. The difference between past and future is not fundamental. It exists only at the macroscopic level, where the second law of thermodynamics operates. Layer 4. Time passes. This is what the Wheeler-DeWitt equation challenges. At the most fundamental level of quantum gravity, time does not appear as a variable. The universe is described by a static equation. Nothing evolves, nothing passes. Layer 5. Time is a single quantity. Even in our everyday experience, time is not one thing. It is many things. Clocks measure duration. Memory records the past. Anticipation imagines the future. These are different phenomena, and they may have different explanations. When we bundle them all together under the single word time, we may be creating a false unity. After stripping away all these layers, Rovelli is left with a question. If time does not exist at the fundamental level, why do we experience it? His answer is elegant and deeply connected to thermodynamics. Rovelli, in collaboration with the French mathematician Alain Connes, developed what is called the thermal time hypothesis. This hypothesis, published in 1994, proposes that what we experience as time is a consequence of our thermodynamic interaction with the world. The idea goes like this. At the microscopic level, the world is described by quantum states that do not evolve in time. But we, as macroscopic beings, do not have access to the complete microscopic description of the world. We see a blurred, coarse-grained, averaged version of reality. And when you look at a system from this blurred perspective, when you do not know the exact microscopic state, but only the macroscopic properties like temperature and pressure, something remarkable happens. There is a natural mathematical flow that arises from the statistical properties of the system. This flow is what we experience as time. In other words, time is not a fundamental feature of the universe. Time is what emerges when a system with limited information, like a human brain, interacts with a system whose microscopic details are hidden, like the macroscopic world. Time is a product of our ignorance. If we could see every particle, every quantum state, every microscopic detail, we would see a timeless world. It is precisely because we cannot see those details, because we see only a blurred, averaged version of reality, that we experience time. Rovelli puts this beautifully. He writes, "Time is the form in which we beings whose brains are made up of memory and anticipation interact with the world. It is the source of our identity. For Rovelli, time is not a property of the universe. It is a property of our relationship to the universe. It is a perspective, not a thing." Now, not everyone agrees with Rovelli. There is a significant counter-argument, and it comes from someone who is in many ways Rovelli's peer and collaborator. Lee Smolin is a Canadian-American theoretical physicist who, like Rovelli, is one of the founders of loop quantum gravity. Smolin and Rovelli have worked together on the same theories, used the same mathematical tools, and published papers together. But when it comes to the nature of time, they have arrived at diametrically opposite conclusions. In his 2013 book, Time Reborn, Smolin argues that time is not an illusion, time is real. In fact, Smolin argues, time might be the most real thing in the universe. Smolin's argument goes like this. Physics has been making a systematic error for centuries, starting with Newton and continuing through Einstein and into modern theoretical physics. We have been treating the laws of physics as timeless mathematical truths. We write down equations, and we assume those equations are eternal. They were true at the Big Bang, they are true now, and they will be true forever. The laws do not change. But Smolin asks, what if this assumption is wrong? What if the laws of physics themselves evolve over time? What if the laws we observe today are not eternal truths, but products of a historical process? What if the universe began with no fixed laws at all, and the laws we see today emerged through a process analogous to natural selection? Smolin calls this idea cosmological natural selection. He proposes that universes reproduce through black holes, each black hole creating a new universe with slightly different laws. Universes that are good at producing black holes produce more offspring. Over many generations, the laws of physics evolve toward configurations that produce many black holes, and, incidentally, many stars, many planets, and many opportunities for life. In Smolin's view, if the laws of physics evolve, then time cannot be an illusion. You cannot have evolution without time. You cannot have change without time. Time must be real, because without real time nothing can truly change. And without change, the laws of physics cannot evolve. Smolin further argues that the timelessness of the Wheeler-DeWitt equation and the block universe are not features of reality, but symptoms of our current theories being incomplete. He believes that a correct theory of quantum gravity will include time as a fundamental feature, not eliminate it. This creates one of the most fascinating intellectual standoffs in modern physics. Rovelli says time is an illusion. Smolin says time is the most real thing there is. Both are brilliant physicists. Both have worked on the same theories. Both have deep knowledge of the same mathematics. And they disagree completely. The scientific community has not resolved this disagreement. Some physicists side with Rovelli. Some side with Smolin. Many are somewhere in between, uncertain, waiting for more evidence, more mathematical results, more experiments. The honest truth is that we do not know who is right. This is an active, open question at the frontier of human knowledge. Now, we have talked about what physics says about time. We have talked about what philosophy says about time. But there is a third perspective that is absolutely crucial, and it comes from neuroscience. Because regardless of what is happening out there in the universe, the time you experience, the time you feel, the flow of moments that constitutes your conscious life, that is generated by your brain. And your brain's construction of time is far more strange and unreliable than you might think. Here is a fundamental fact that most people do not realize. You have eyes to see, ears to hear, a nose to smell, a tongue to taste, and skin to feel. Each of your senses has a dedicated organ, but you have no organ for sensing time. There is no time receptor. There is no temporal nerve. There is no time cortex in the brain dedicated exclusively to perceiving time. Your brain constructs the experience of time from scratch, using information from other senses, from memory, from attention, and from internal neural processes. Time, as you experience it, is a construction. It is assembled by your brain, not perceived directly by a sense organ. This has profound implications, because constructions can be wrong, they can be distorted, manipulated, disrupted, or broken, and indeed, the brain's construction of time is distorted all the time. Consider the present moment. Right now, you believe you are experiencing the present, but you are not. What you experience as now is actually the past. Your brain receives sensory information at different speeds. Light travels faster than sound. Touch signals from your toes take longer to reach your brain than touch signals from your face, because your toes are farther away. Visual processing takes longer than auditory processing. If your brain presented sensory information to you as it arrived, your experience of the world would be a disordered mess. Sights and sounds would be out of sync. Your own body would feel fragmented in time. So your brain does something remarkable. It waits. It collects sensory information from all sources, waits for the slowest signals to arrive, and then stitches everything together into a coherent snapshot that it presents to your consciousness as now. The present moment you experience is not actually the present. It is a reconstruction created by your brain based on information that is anywhere from 80 to 500 milliseconds old. You are always living slightly in the past, experiencing a polished, edited version of reality that your brain has assembled for you. In the 1980s, the neuroscientist Benjamin Libet performed a famous series of experiments that revealed something even more disturbing. Libet asked subjects to perform a simple action, like pressing a button whenever they felt like it. He measured the timing of 3 events: the brain activity associated with the decision, the subject's conscious awareness of deciding, and the actual pressing of the button. What he found was remarkable. The brain activity associated with the decision began about 350 milliseconds before the subject became consciously aware of having decided. In other words, the brain had already initiated the action before the person felt like they had decided to act. The experience of deciding, of choosing, of willing an action came after the brain had already set the action in motion. This does not necessarily mean that free will is an illusion, as the interpretation of Libet's experiments is hotly debated, but it does tell us something important about the brain's construction of time. The sequence of events, as your brain presents them to your consciousness, does not necessarily match the sequence of events as they actually occur. Your brain can edit, rearrange, and reconstruct the temporal order of events before you become aware of them. Time distortion is something everyone has experienced. When you are in a life-threatening situation, like a car accident or a fall, time seems to slow down dramatically. People who have survived such events often report that everything seemed to happen in slow motion. For years, researchers assumed that the brain actually speeds up its processing during extreme danger, effectively creating a slow-motion experience by processing more information per second. But in 2007, neuroscientist David Eagleman tested this assumption with an ingenious experiment. He had volunteers free fall from a 150-foot tower into a safety net, a genuinely terrifying experience, while wearing a special device on their wrist that displayed numbers flickering faster than the eye could normally read. If the brain actually sped up during fear, the volunteers should have been able to read the numbers during their fall. They could not. Their temporal resolution did not increase. Time did not actually slow down. What Eagleman found instead is that during extremely frightening or novel experiences, the brain creates much denser memories. More details are recorded, more information is stored, and when you later recall the event, the density of those memories makes the event feel like it lasted much longer than it actually did. The slow motion effect is not happening in real time. It is a retrospective illusion created by memory. Your brain is not slowing down time. Your brain is changing how it remembers time. This is just one example of many. Time drags when you are bored because your brain, lacking stimulation, turns its attention to time itself. And this focus on the passage of time makes each moment feel longer. Time flies when you're engaged because your attention is absorbed by the activity and not monitoring the passage of time. Time seems to speed up as you age because, as you get older, you have fewer novel experiences, and novelty is what creates dense memory formation. A day at age 7, filled with new discoveries, feels much longer in retrospect than a day at age 47, which is largely routine. Even more dramatic distortions can occur in neurological conditions. People with certain types of brain damage can lose the ability to perceive time altogether. Patients with damage to the cerebellum, which plays a role in timing, can have severely impaired time perception. People experiencing certain psychiatric conditions, such as dissociation or derealization, often report that time feels unreal, frozen, or moving at the wrong speed. People under the influence of certain substances report time stopping, reversing, or losing all meaning. All of this tells us something crucial. The time you experience, the flow of moments, the feeling of now, the sense of past and future, is a product of your brain. It is neurologically constructed. It can be distorted, disrupted, and broken. This does not necessarily mean that time does not exist in the external world, but it does mean that what you experience as time is not a direct window onto external reality. It is a neural construction, and the relationship between this construction and whatever is actually happening in the universe is far from straightforward. And this connects directly to Ravelli's argument. Ravelli says, that time emerges from our coarse-grained, blurred interaction with a world whose microscopic details we cannot see. Neuroscience is telling us something similar from a completely different direction. The time we experience is a construction of a brain that receives incomplete, delayed, and processed information, and stitches it together into a narrative that may or may not correspond to fundamental reality. Now, let us turn to the experimental evidence, because no matter how elegant the theories are, no matter how persuasive the philosophical arguments, science ultimately comes down to what we can test, measure, and observe. So, what does the experimental evidence actually tell us about the nature of time? We have already discussed the experimental confirmations of time dilation, the Herfel-Keating experiment, the muon lifetime measurements, the GPS relativistic corrections, the NIST optical clock experiments. These are all rock-solid experimental results that confirm beyond any doubt that time is not universal, not constant, and not absolute. Time is relative, flexible, and dependent on gravity and motion. But these experiments do not directly tell us whether time is fundamental or emergent. They tell us that Newton's time is wrong, but they do not tell us whether Einstein's time is the final answer. The Page-Wouters experiment of 2013 comes closer. By demonstrating that the appearance of time can emerge from quantum entanglement in a system that is globally static, this experiment provides direct evidence that time does not need to be fundamental. It shows that a timeless universe can give rise to the experience of time for observers within it. This is not proof that our universe is timeless, but it is proof of concept. It shows that it is possible for time to be emergent rather than fundamental. There is another experimental development that is worth mentioning, not because it directly addresses whether time exists, but because it reveals how strange the structure of time is at the quantum level. In 2012, the Nobel Prize-winning physicist Frank Wilczek proposed a new state of matter called a time crystal. In an ordinary crystal, like a diamond or a snowflake, atoms are arranged in a repeating pattern in space. The crystal has spatial periodicity. Wilczek asked, could there be a system that has temporal periodicity? Could there be a system that repeats in time the way a crystal repeats in space? At first, this idea seemed impossible. A system that oscillates forever without consuming energy would seem to violate basic physical principles. But in 2016 and 2017, two independent research groups, one at Harvard University led by Mikhail Lukin and another at the University of Maryland led by Christopher Monroe, created time crystals in the laboratory. These are systems of interacting quantum particles that oscillate between states at a regular interval, not because they are being driven by an external force, but as their lowest energy state. They break time, translation symmetry, meaning their behavior is not the same at every moment of time, even though the underlying equations are. Time crystals are a genuine new state of matter. They have been verified experimentally, and research on them continues to advance. In 2025, researchers at the Vienna University of Technology discovered that quantum chaos can give birth to time crystals, a previously unexpected connection. Time crystals do not prove that time is an illusion, but they show that time has structural properties at the quantum level that we are only beginning to understand. The relationship between time and matter is more intimate and more strange than anyone imagined. There is one more experimental frontier worth discussing: the question of whether time is continuous or discrete. In our everyday experience, time seems to flow smoothly. There are no gaps, no jumps, no individual frames, but several theoretical frameworks suggest that time might actually come in discrete chunks, much like energy comes in discrete quanta. In loop quantum gravity, space-time itself is quantized. It is made of tiny discrete loops or nodes, and the smallest meaningful unit of time is related to the Planck time, approximately 5.39 times 10 to the power of negative 44 seconds. This is inconceivably small. It is the time it takes light to travel one Planck length, which is about 1.6 times 10 to the power of negative 35 meters. Below the Planck time, our current understanding of physics breaks down completely. We do not know what happens at those scales. Some physicists believe that time is smooth and continuous all the way down. Others believe that below the Planck time, time ceases to exist in any meaningful sense. The concept of a chronon, a quantum of time, has been proposed but remains speculative. We do not yet have the experimental tools to probe these scales directly. But the theoretical hints are tantalizing. If time turns out to be discrete, it would behave less like a flowing river and more like frames of a film, individual snapshots that, when played in rapid succession, create the illusion of smooth motion. And this would bring us remarkably close to Barbour's picture of nows in Platonia, static, individual configurations that we string together into a narrative of time.